Hello, good morning. I hope you are doing well today.
Good morning.
Today we are looking at fluids for our lab. I don't think any of the lectures, the lecture 1510 lecture has gone to as fast as fluids. So we'll have to go through some of the ideas and concepts before we can do this lab. So we know that when you drop something in the fluids, it's going to feel a drag force. So in physics, we consider both the air and liquids to both be fluids. When we do fluid dynamics toward the end of the semester, we mean either air or liquid. Both of them are considered fluids. As long as they're not solid, there are fluids. So for this lab, we are going to evaluate and measure the drag force when you drop something either in air, which is part 1, or drop something in the liquid, which is the part 2. So air, the drag force a lot of time is called, when we drop something in the air, it's called the air resistance. It is when the object moves in the fluid in certain direction, then the object will experience a force acting in the opposite direction to its motion. And we call this resistance force to be a drag force. It depends on a variety of different factors. For example, viscosity of your fluid, the density of your fluid, what size of your object it is, and speed of the object. The faster the object moves, the greater of a drag force the object will experience. So in this lab, our goal is to look at exactly the relationship between our drag force and the speed. How do they relate? Is it the drag force is related proportional to simply the speed in a linear way? Or is it proportional to speed squared? Or is it speed to the power of 3? This is what we're trying to measure. The first part, we simply are evaluating dropping something in the air. We drop a bunch of different coffee filters and measure its velocity after it's falling for some distance in the air. So that the thing about the trick that we do is we wanted to only measure it when it reached terminal velocity. So what is terminal velocity? Meaning that when you drop something, first of all, it's going to accelerate at first, right? Because you have gravity. But once your air drag becomes bigger and bigger, because as you drop, the velocity increase. As your velocity increases, the air drag also increases because F is proportional to the velocity. When your air drag had reached to a magnitude so that it's exactly equal to the weight of your object, so when F of drag is equal to mg, the gravity of your coffee filters, then you can see that the two forces balance out, giving us no acceleration. So this object can no longer accelerate because the total force is 0, right? F net is 0. So when any object experiences a 0 acceleration, it's going to continue dropping with that terminal speed. So it's terminal, meaning that the velocity can no longer increase. It will simply drop with that constant velocity. Now, why do we want the object to reach the terminal speed to measure that? Because here we're trying to measure the drag as a relationship to the velocity to a certain power. We don't really know what that relationship is. So we need to measure this and this separately. It's easier to measure velocity, right? You all have different devices. Even if it's accelerating, we still could use a photo gate if we need to. But it's very hard to measure a drag force, right? There's no device out there we can feel unless we build some sensors on our coffee filters, which will be very hard to do. We cannot really measure this drag force. That's why we go to terminal velocity is Once the object reaches terminal velocity, the drag force, we know the drag force is equal to its weight. And the weight of something is easy to measure. So we are measuring the weight as an indirect measure for the drag force. That is the reason. So how can you make sure an object always reach terminal speed? Well, give it enough time. So the velocity has enough time to increase. Eventually, it's going to reach its terminal velocity, right? So what we do is we simply drop the coffee filters from a very high distance. And eventually it's going to, when it's falling on the ground, it's going to reach terminal speed. Make sure that it's a long fall. So if we were to do this in person, we would even consider dropping the coffee filters where we have ourselves standing on the chair, on the table, so that we are very high, and then we let go of the coffee filter. So make sure that it's indeed a long fall. So eventually it reaches terminal speed. So that's part A. Okay. And let's take a look at our the math. So we can see exactly how we are going to do the plot. The goal of the lab is to find the relationship between the drag force and its speed. When we don't really know the relationship, we can write it down in a very generic format. Let's say FD is equal to V, but we don't know to what power, right? So we're going to say V to the power of N. And also there might be some constant, so we multiply that by a constant C. We don't really know what C is. We don't really know what N is, and that is what we're trying to measure. And there's also a, this is a very common practice in doing graphing, graphical analysis, is when you have a power relationship, when you do the plot, it's not going to be a straight line. This is not a linear relationship, right? But we can turn this into a linear graph by taking a log of this function. So if you take the natural log on both sides, the left side become log of FD, the right-hand side become log of C times V to the power of N. So when you know that when you have something times something, log of A times B is log A plus log B, right? So this can be rewritten using log C plus log of V to the power of N. And we also know when you have V to the power of N, you can write N in front, so N times log of V. So this had become a linear relationship. Okay, so let's take a quick look at our pre-lab, which is exactly what we are showing here, but with some numbers. So let's say you are looking at a relationship between two different variables, R and D versus D. And you're trying to graph the log of R versus log of D. Okay, so log of R is log of C plus N times log of D. So if you were trying to graph this is your Y, log of D is your X. So Y is equal to KX plus B, right? This is a linear relationship. And as your data reflected, you have, you got this equation. So from this data, can you tell me what is your N and what is your C? First of all, can you tell me what is your N?
Is it 1.998?
Yes, that's just the slope, right? The slope times X, this is your X, and N is your slope. So N is 1.998. So we measured, now we have found N using our data. And what about your C?
Is it 10 to the power of negative 1.769?
Right, so we will say the log of C is negative 1.709. So we write it in this format, but this is not a base 10 log. This is our natural log. Okay, so C is e to the power of negative 1.769. So that's our C. This is our N. So from our data, we're able to find these constants, and that's how we're going to do this in the lab.
So when a problem just states log, do we just assume it's natural log?
Yes, yes.
All right, thank you.
Thank you. Okay, so let's get back to our experiment. All right, now we know what do we need to measure. We need to measure different drag forces. We need to measure the velocities, and we're going to plot, take the log of them and do the plot to find our y-intercept, to find our slope. So this is what we're trying to do. We'll take a look at our data sheet. So we can do this for different numbers of coffee filters, because as you drop different numbers, they will all eventually reach different terminal speed. So we're going to do 1 or 2 or 4, 7, and 10 different coffee filters. And the drag force is measured by the weight indirectly, as I said earlier. And that is easy. You simply put your coffee filters on the scale and you can read its mass. So you can see that we actually, the data will only give you when you have 10 coffee filters on the scale. Measuring 1 is not as accurate because it's very light. So we measure 10 instead, and you can figure out what 1 will be and what 2 will be, what 4 or 7 will be. So we only need to measure the mass 1 time. The more time-consuming part is to measure the speed. And we know that, well, eventually it has already reached terminal speed, especially if you drop it from a very high distance. So we are observing doing a fall for 2 meters when we line up 2 different meter sticks on top of each other against the wall. I'm going to time it, how long it takes for the coffee filter to fall down for 2 meters. So we can take 3 different trials for each of the number on how much time it takes and calculate the velocity. Now, if it's terminal velocity, which means speed remain constant, velocity is simply distance over time. So that's easy to measure. All right, so let's go to our video and take a look at how that was done. Okay, so now they're going to drop objects in air. So I want to say, in your real life, we will do the stopwatch ourselves, right? We have to time it when we reach the top end of the 2 meters, and we click our stopwatch again when we reach the bottom end. But since we have this video recorded, they actually already added a stopwatch for us, just for the first part 1. So you already have stopwatch, digital stopwatch synchronized when the coffee filters is at the top. So all we need to do is simply to stop and pause and read how much time it is when we reach the bottom. So let's take a look.
In the second part of the lab, the objects will move slow enough through the oil for you to do the start and stop for yourself.
Okay, so you see that this is what the data collection will look like for part 1. The stopwatch is already built in. It's synchronized at the top. So all you need to do is to pause it when you reach the bottom. So you could view, focus your eyes on the left-hand side, the smaller view, or you can focus your attention on the more zoomed in view. But to be consistent, because when you look at the zoom in view, you tend to stop the watch a little bit later than if you were looking at the zoomed out view. Both are fine, both of them are fine, but if you choose one way, just stick with it. So let's say I was looking at the zoomed in view where I looked at the blow up picture. So I hit my pause button as soon as the coffee filter is at the ground. So I recorded the time for that fall is 2.27 seconds, and you can write that down in your data sheet. So let's all do this for the one coffee filter as a practice. Okay, so this is your one filter. All right, so, well, if I'm stopping it, you're all gonna get the same number, obviously, but if you were to do this by yourself, everybody will have stopped differently and you get different trials. So the first trial I had got 2.56 seconds. And they're dropping the second trial. I got the same, and if it's the same, it's okay. You simply just record it honestly. That's the third trial, I get 2.46 seconds. So that's your 3 trials for the one coffee filter. Okay, let's go back to our data sheet to see how the speed is being entered and calculated. For each of the time trial, you calculate a different speed, right? So for the first one, the speed would have been 2 meters divided by 2.5 seconds, and you will put that in your speed. And you did that. You will do that for the other trials. So all of this will give you an average speed, right? Calculate average speed. To get the uncertainty in your speed, you know that, okay, V is D times T. Using, remember our arrow propagation, there were 4 rules we used in the beginning of the semester, the very first lab. The last rule says you can have simply a known number multiply or divide by another variable. The other variable is simply the absolute value of V is simply the known number multiplied by the absolute value of your delta t. So, okay, so let me write it a bit clear here. Delta V is D times delta t. So using this uncertainty propagation rule, we know that, well, to write down our delta V, we need to figure out the uncertainty of our delta t. Okay, so you have 3 different trials. How do we get our delta t? Delta t is equal to, still recall how to do the uncertainty in delta t? So you did the measurement 3 times, you get a range of answers. Some of them are bigger than the other. So how do you get the uncertainty of those numbers?
It's maximum time minus minimum time over 2.
Very good. Thank you, Peter. It's max minus min over 2. So in this case, for the trial that I just did is 2.56 minus 2.46 divided by 2. So that's my uncertainty for the time. Now, everybody do this lab will get a different uncertainty yourself. So for that first number of filters, we found delta t, and we can multiply by that 2 meters because D is 2 meters for all of them. Simply multiply that, you get uncertainty here for the speed. Okay, you can repeat this for the different number of coffee filters, and the procedure is the same. As you have more numbers of filters, do you expect to record your time, more time or less time? What do you expect? More time for the fall or less time for the fall?
Less time.
You will have less time, very good. So let's go, because as you increase the weight, right, compared with the air resistance, the weight is more, so we'll have give it a bigger acceleration. and overall it will take shorter time to fall. So you can do the rest of them. I just wanted to remind you of the last data where they dropped 10 coffee filters. So if you do, you will notice that, okay, the data works out very nicely. You see a obvious decrease in the time of the fall from 1 to 2 to 4 to 7. But then you will notice when they drop the 10 coffee filters, the time actually increased from the 7 coffee filters. So that wasn't right. So by looking at this more carefully, you notice that that was because the digital clock was not synchronized at the time. I don't know if I could stop exactly, but I had it looked at this earlier. Let me try to stop it for the second time. Okay, so you can see that it was not synchronized at the beginning of the fall. So that is the reason why the data you're going to record for the 10 coffee filters is actually longer than it should be. So to correct for that, I want you to deduct the number of times, the number of seconds by 0.6 seconds. So normally you will read, okay, you will read, let's finish this fall. 1.56, right? So instead of writing 1.56 for your time, I want you to minus 0.6 seconds to correct for that mistake. And that will give you better data. Okay, so you will write 0.96 seconds for the first trial for your 10 coffee filters, right? So minus 0.6 for all of your data you record for the 10 coffee filters. Everything else is good. Everything else is correct, but just the last data point, the digital clock was not synchronized. So correct for that. All right, so as you have your data, okay, so you would, I want to bring up, just want to show you as an example what we will do once we have our data. So I encourage everyone to plot using your computer instead of using hand. In fact, this one is very hard to do by hand. Okay, so you have a list of F versus D, right? FD, your velocity data, your drag force data, you enter them, right? For number of filters, 1, 2, 4, 7, 10, you fill out these columns, and then you need to make a two new columns for log of V and log of FD, because you're plotting the log, not the variable itself, right? So you can do a log function and simply let that spreadsheet to fill it out for you. So once you have these two columns, you're going to highlight it and you're going to do a plot. Okay, so a scatter plot. So once you have this data, you're going to, now I don't have any data, you're going to select, now I couldn't really do anything because I don't have any data. But as the option will give you, once you collect the different plots, different dots, is going to show you add equations, and you can add your equations. Okay, so I just wanted to emphasize, don't forget this step when you do the plot. So when you get your equations, which should be a linear equation, you can read the slope and you can read the y-intercept. Okay, the slope is the n, and the y-intercept will give you that constant c. If you take the e to the power of that, it will give you the constant. So eventually in your data sheet, you should tell us what is the relationship that you find. How is your drag force related to velocity? Which one of these is correct as indicated by your data? Okay, so that's our part 1. Part 2, we are dropping objects in liquid, not in air. So we do is we have these different small spheres and we let them drop in the oil. Oil is the liquid we're evaluating. So the thing that is different by dropping something in the liquid is other than the drag force, you still have the drag force, of course, but liquid also provide a buoyant force. Now, this is from a previous question, previous lab is when your object displaces a certain amount of liquid, there is a floating force provided by the liquid, right? So the buoyant force is always there, but the drag force is only there when the object is moving, has a velocity, right? So here our resistance consists of two parts, drag force and buoyant force. Both of them are pointing upward, right? So that is what is a little bit different when you drop something in liquid. These two add up. Now this is a total force, it's not a new force. F of B plus F of D add up to be the total resistance, and that is equal to the weight of these spheres when it reaches terminal speed. Again, we're looking at what happens at terminal speed when these three forces add up to be zero, right? So when F net equals zero, acceleration is zero. Here, F net consists of two parts, mg and buoyant force and the drag force added together. Okay. All right, so let's take a look at our equations. So here for dropping spheres, we already tell you, we simply just tell you it is a linear relationship between the drag force and your velocities. So this is a given. Okay, so we know previously we were looking at how drag force is related to velocity. Here, we already tell you it's C times V. What is interesting is you're going to try to find your buoyant force. Okay, so your total resistance, which is equal to mg, is going to be the drag force times the buoyant force. So you're going to plot mg is equal to C times V plus F of B. Okay, so this is your y, this is your x that you measure, and this is your y-intercept. Okay, so your y-intercept, so the slope here give you the constant C, your y-intercept here give you the buoyant force acting on your sphere. You could use what you measure here, your y-intercept, to compare with the buoyant force calculated using Archimedes principle, which is something we have learned from our previous lab, to see if they are indeed agreeing with each other. Okay, so here in the second lab, we can measure the buoyant force using our data. Okay, so exactly how y is recorded, how x is recorded. We already know how x is going to be recorded. That's velocity. We're using our stopwatch to take the time and we find our velocity. The y is our weight, is the weight of those beads. And that simply can be calculated by using the density of these different materials multiplied by the volume. So we're going to use the same dimension for all of the beads. They all have the same dimension. They're all of a diameter of 1/4 inch. Okay, so you can find the volume for all of the different materials and you multiply the volume by the corresponding density and they have different weight. So this is something we already did in our pre-lab. For example, the second one is marble with this particular diameter, and we want to calculate the buoyant force. Okay, all right, so let's see how we calculate the buoyant force in this case. F of B is equal to, you still remember how to calculate the buoyant force acting on the marble provided by the oil. F of B is equal to, anybody still recall?
Is it fluid density times acceleration of gravity times volume?
Very good. The liquid density times the volume of the amount of liquid that is being displaced times little g. Excellent. So this is the weight of the fluid that's being displaced. So since here we are using oil, liquid, we use the liquid of the oil. And how much oil is displaced depends on what object you immerse it in it, right? Here we put a marble in it. So the volume of the liquid is equal to the volume of the marble times G. Oil density is given, volume of the marble can be calculated given by the dimension, sorry. The radius is 1/2 of the diameter, and that's a 1/8 of an inch, right? And 1 inch is 2.54 centimeters. So you can calculate what the radius is and plug in into your equation to find the volume, and you can find the Bourne force. And this is also what you need to do in the lab is the Bourne force as you measure, which is the y-intercept, can be compared to the Bourne force you calculated using Archimedes' principle. And I have just showed you, you can calculate F of B using Archimedes' principle and compare with what you would have obtained from your data. Okay, so this is the weight, right? The mass can be calculated simply using the density times your volume for individual different objects. They all have the same volume, but they have different density. So you're going to use different density to multiply by that volume. That's your Y. It's your data for your Y. Your X is your data for your speed. And time it in the liquid is easier, and that you actually do it yourself because it's slow enough. And you don't have to rely on a digital stopwatch. There is not a digital stopwatch. So they give it a 30 centimeter fall. You can see they put a little ring on this. You're going to start your stopwatch when your marble passes through the ring up there, and you're going to stop it at the end. So for a centimeter distance, for example, this is what will look like for the first object, the plastic. Now you could do your stopwatch and just see what it is. Okay, so I just started my stopwatch when your bead passed through that ring. And then you can look at the bottom, which the more zoomed in view on the right hand side, and stop, pause your watch when it's reached the bottom. So this is, you can see this is slow enough, and we can do this ourselves. All right, it's approaching the bottom now. I'm going to pause it once it reaches the bottom. Okay, so I had just taken one data and I got 50.50 seconds. So that is the time I got. Anybody else got your time? Anybody also use your stopwatch to time that? So this is the time I got. You'll do this for 3 different trials, and you have 3 different times. Use the same method to calculate your speed. But now be careful that your fall is velocity is d over t is 30 centimeters. Okay, so it's 30 centimeters divided by the time. And again, I want meters per second is 0.3 meters divided by the time. Okay, so use that distance for calculating velocity of dropping these different spheres in your liquid. Okay, so that you're able to put in all of the speeds in, and then again, uncertainty, you can see delta V is D times delta T. And again, D now is 0.3 meters. Okay. So previously it's 2 meters, now it's 0.3 meters. So that is a different number you have to be paying attention to here. So that will conclude your data collection, and then you're going to plot it. The plot here does not require taking a natural log, because we already tell you it's a linear relationship with V. As your data will show, it is a linear relationship. You don't have to take the log. You can plot a V versus f of r directly, okay? And you will get an equation from your data. So read the slope and y-intercept from your equation, in particularly compare your y-intercept, which is your Boyne force, with the Boyne force that you could have calculated from your Archimedes principle. Okay, so that's the last part of this data collection. All right, so that's all. That's all for this lab. Are there any questions so far?
For the uncertainty in the speed of part 1, we just multiply it by 0.2, correct?
Yes, by distance. Our distance for that fall is 2 meters, just multiply by 2, just 2.
Okay,
Yeah,
and then
double that, yeah. Just 2.
and then I know that for the second one, you changed the top for the distance to 2. So is it 2 or is it 0.2?
For the second one, the total distance of the fall is 30 centimeters. So you do 0.3.
Okay.
Yeah. So first one, distance is 2. Second one, the distance is 0.3. Any other questions? All right, if you do have any more questions later on, feel free to email me. Otherwise, I will see you guys next week. We have 2 more labs. I believe we have 2 more labs after this. So really, yeah, we're just hanging there. We're coming close to an end. All right, have a good rest of your week. See you guys next Monday. Bye, everyone.
Take care.
Thank you, you too. Okay, so this question, for the uncertainty of time, do we do max minus min over 2? Yes, you do max minus min over 2 for the uncertainty of the time, and you multiply that uncertainty of the time by the distance, either 2 meters or 0.3 meters, to get the uncertainty for the speed. Yes. Okay. Bye-bye, everyone.
Just to make sure, there's still school on the week of the 22nd, right?
Yes, that's the Thanksgiving week. We always have class Monday, Wednesday, and Monday, Tuesday, and Wednesday. And
Okay.
yeah, school will be off Thursday and Friday.
All right.